And the goal is to find the work done by this force field, f of x, y, z equals negative 1 half x, negative 1 half y, 1/4, on a particle that moves along this helix, r of t is cos t sine t t, from the point 1, 0, 0 to the point 1, 0, 3 pi. So if that's the case, can we see what t ranges from? What sense does this make? Where is t ranging from? Well, you'll notice the third slot is t, starts at 0, it ends in 3 pi. So that tells me then that t ranges from 0 to 3 pi. Certainly cosine of 0 is 1, 0. Cosine of 0 is 1. Cosine of 3 pi is the same as cos of pi is negative 1. Sine of 0 is 0. Sine of 3 pi is 0. So we know that to be the case. Now, let's recall what is work is the integral over c of f dot dr. So we have the work as the integral over c. F we have there as negative 1 half x, negative 1 half y, 1/4 dot dr. Now dr is going to be what? Dr is going to be dr dt dt. Dr dt is the velocity. So what is my velocity? We see r of t is cos t sine tt. The derivative of cos t minus sine t, the derivative of sine t, cos t, the derivative of t, is 1 dt. So we go ahead and make that change. So we have negative sine t cos t 1 dt. So now I've got to change this from c to t, integral as t goes from 0 to 3 pi. Negative 1 half x, what is x? Cos t. Comma negative 1 half y, what is y? Sine t. Comma 1/4 dot negative sine t cos t1 dt. So here's our integral. So let's go ahead and multiply that out and see what we get. In our first slot, negative 1 half cos t times negative sine t, negative times negative positive 1 half cos t sine t. In our second slot, negative 1 half sine t times cos t is negative 1 half sine t cos t. And in our third slot, 1/4 times 1 is just 1/4. And all of this is dt. So simply this becomes the integral as t goes from 0 to 3 pi of 1/4 dt, which is 1/4 t as t goes from 0 to 3 pi, which is 1/4 3 pi minus 0, which is 3 pi over 4. So that wasn't so bad, but we're going to show an alternate way to solve this problem. So here's my vector field, and I'm interested in the curl of that vector field. And we remember that is the gradient operator crossed with the vector field f. The gradient field operator is, of course, partial with respect to x, partial with respect to y, partial with respect to z, crossed with f here, negative 1 half x, negative 1 half y, 1/4. So let's look at that curl of f and see what it gives us. So there's our matrix. So what do we get in the I direction? We get partial of y, partial of z, negative 1 half y, 1/4. In the j direction and in the k direction. So doing our computation, curl of f in the I direction, partial with respect to y of 1/4, 0, minus partial with respect to z of negative 1 half y, also 0. So nothing in the I direction. In the j direction, minus partial with respect to x of 1/4, 0, minus partial with respect to z of negative 1 half x, 0. And then in the k direction, partial with respect to x of negative 1 half y, 0, minus partial with respect to y of negative 1 half x. That's 0. Curl f is the zero vector, 0, 0, 0, which means the vector field is irrotational, or equivalently, the vector field is conservative. So there is that vector field. Again, curl is 0, it's irrotational, it's conservative. That means this vector field has a potential function such that what? Such that the gradient of that potential function little f equals that vector field big F. Let's find it. So our vector field is negative 1/2 x, negative 1/2 y, 1/4. Our function is f of x, y, z. We want the gradient of little f to equal big F. What is the gradient of little f of x, y, z? What is it? Well, it is the partial derivative with respect to x in this slot, partial derivative with respect to y in that slot, and the partial derivative with respect to z in that slot. So let's build this from this information. So we start with the fact that the partial derivative of f with respect to x is negative 1/2 x. So if I integrate that, f would be negative 1/2 x squared over 2 plus something. Now, what is that something? On a regular integral, it'll be plus a constant. But here, y and z are considered constants. So it's any function of y and z. So what we get here for our function f is negative 1/4 x squared plus g of yz. So keeping that in mind, then what is f sub y? Would be the partial derivative with respect to y of that. Partial derivative with respect to y of negative 1/4 x squared plus g of yz. Well, the partial derivative with respect to y of negative 1/4 x squared is 0. But the partial derivative with respect to y of some function g that is a function of both y and z is just g sub y. We see that. But what do we know? We know f sub y has to be negative 1/2 y. So if that's the case, what does that tell me? That tells me g sub y has to equal negative 1/2 y. So integrating with respect to y, what is that going to give me then? What is g of yz? That's negative 1/2 y squared over 2. Again, not plus a constant, but plus a function of z. So let's call that h of z. So we get our g of yz is negative 1/4 y squared plus h of z. So let's continue. So we saw previously that f was negative 1/4 x squared plus g of yz. So that'll be negative 1/4 of x squared plus what we just said g of yz was, which is negative 1/4 y squared plus h of z. So we're getting close to that potential function. We're going to want to go ahead and take the partial derivative of this with respect to z. So let's do that. So here's where we are. So f sub z, the partial derivative with respect to z of this piece is 0, minus the partial derivative with respect to this piece is 0. The partial derivative of h of z, that is just a function of z, so the partial derivative of a single variable thing is just the derivative of that. So we're seeing that f sub z is h prime of z, but looking up here, we said f sub z was 1/4. So 1/4 is h prime of z. So h of z would be the integral of 1/4, which is 1/4 z plus a constant, but I can go ahead and leave that constant as 0 since I'm just looking for a potential function. So my claim is f of x, y, z, which equals negative 1/4 squared minus 1/4 y squared plus h of z plus 1/4 z is a potential function for that vector field. but we should check that to make sure that that actually works. So that's a potential function for that vector field F, which is negative 1/2 x, negative 1/2 y, a quarter. So let's take a look at that and see what we get. So what is the gradient of F? In the x direction, negative 1/4 times 2x. In the y direction, negative 1/4 times 2y. And in the z direction, 1/4. So that the gradient of F is negative 2/4, negative 1/2 x, negative 1/2 y, negative 1/4, check. Indeed, that matches. So little f is the potential function. We knew we'd be able to find one because it was irrotational. The curl was 0. It's a conservative vector field. It will have a potential function. So recall this was our original question. We wanted to find the work that was done. Now we found the potential function. We said that was f of x, y, z equals negative 1/4 x squared minus 1/4 y squared plus 1/4 z. We can actually use that potential function to find the work. Now, just to show you that it's going to give us the correct answer in this situation, I'm going to evaluate the potential function at the ending point and the beginning point and subtract. So what is the potential function at the ending point? What is f of negative 1, 0, 3 pi? What does that equal? You get negative 1/4 plus 3 pi over 4. How about the starting point? And if I subtract those, f of the endpoint minus f of the starting point is 3 pi over 4, which you may recall was the answer to the original question. And this helps us imagine the behavior of the fundamental theorem of line integrals. So this is going to be like the fundamental theorem of calculus. You find the antiderivative, evaluate at the endpoint and the starting point, and subtract. The same kind of idea works here. We find the potential function, evaluate at the endpoint and the starting point, then subtract. But this only works if a potential function exists. And when does a potential function exist? If the vector field is irrotational, i.e. conservative, then we know we can find a potential function and subtract accordingly. So I want to conclude by stating informally the fundamental theorem of line integrals. So if we have a conservative vector field, so how can we determine if a vector field is conservative? It has a curl of 0. It means it's irrotational. So if f is a conservative vector field and if the curve that we're dealing with is nice, so it can't be too crazy, the kinds of things we've been working with, piecewise, smooth, etc., then work is simply f of the endpoint minus f of the starting point, where little f is the potential function for big F, which means, of course, that little f has a gradient that equals big F. So for a conservative vector field, for a reasonable curve, the work will simply be the potential function evaluated at the endpoint minus the potential function evaluated at the starting point. Again, notice how that is similar in many ways to our fundamental theorem of calculus.